Uh, Hello everyone. Can you see the screen?
Yes,
Can you see
yes,
my
yes, we
screen?
can
The
see. Yes,
presentation?
we can see.
Okay.
Yes, we can see.
Okay. So first of all, I'm here to give you an idea about designing your algorithms and prototyping your FPGA or SoC on MATLAB and Simulink. So so this is the agenda I'm going to follow. Like, what are the challenges? What we have proposed? What we have the solutions? How we can generate the synthesizable VHDL Verilog code, and how we can do the verification for that. So before going to follow the agenda, I'll just like to show you a very simple demo. So okay, so for that you just need MATLAB software and some hardware support packages, which I'm going to tell you like how you can get it. So first we open the MATLAB window. Here we if you have any doubt in between, you can ask me in between also. So we go to the add-on packages. We go for the get hardware support packages. So suppose if you are working, so okay, so how many of you have I suppose that most of the people, you are working in hardware or like planning to work on hardware. So for that, you if you're working on Xilinx, if you're working on Altera, if you're working on Microsemi, you can get add-on packages for most of the hardwares here. And if you have your custom board, that can also be present in the in MATLAB, so you can also design the packages. So here, like Arduino board is there. So suppose if I'm using the Xilinx hardware board, I'll just check the Xilinx board. So for that, you need HTL coder support package, SoC block set, or anything which whatever you want to implement basically. So this is where you get the hardware support packages. But before going deep into the hardware support packages and hardware, I would just like to tell you that tell you that how we can generate the VHDL code in just like seconds. So for that, you just need a MATLAB software. I'm just going to show you a very basic simple example of FIR filter, fixed coefficient FIR filter, which is a shipping example. You can easily implement it in your MATLAB window also. So for that, I will just type SFIR underscore fixed and click enter. Yeah, just a minute. So it will open a Simulink window. Yeah. So it will open a Simulink window or of fixed FIR filter, where you can see that I am giving fixed coefficients as an input. I'm giving in high impulse pulse as an input to the filter. Here, if I open the block, we can see that there's multipliers, adders, and basic building blocks of FIR filter. So it's a very easy design to start with. Then if you see the output, here I'm having the filtered output. Here I'm having just the delayed output to see like our signal is passing through or not. So I'll just quickly run the simulation. Here you can check that what is the output. So okay, yeah, so this is basically your delayed output. This is your high impulse, and this one is your filtered output. So this is a low pass filter. That's why it passes the lower frequencies and it suppresses the higher frequencies. So what do you think that how, like, if we have our model ready, if we have our transcript ready, then it we need another people to write a VHDL or Verilog code. We need another people to verify it. We need students to generate test bench for this. So it takes a lot of time, it takes a lot of efforts, and multiple students, of course. So from here I can directly do that within seconds. So like how I can do it, I'll just go to the HTL code. I'll just go to the generate HTL for subsystem. Now if you check in the command window, it will just start. Just a minute. Yeah, it'll just start running the generating HDL for fixed point for SFIR fixed, and after that it will generate the VHDL code automatically. Okay, so yeah, let the process be completed. So yeah, you can see here when I run the simulation, it creates a folder named as SLPRJ, which is Simulink project. When I generate the HDL code, creates a folder named as hdl underscore brj. Okay, so we can check that we have generated the vhdl and verilog code just like in 1 or 2 minutes, in 1 minute. So this is the basically normal HTML code which you generally write for a fixed point FIR filter or like this. So now this is just a quick demo of like how we can generate VHDL Verilog code automatically. Now I'll go on the presentation and will show you how we do it. So okay, so yeah. So the main thing is if we use the traditional implementation workflow, suppose you have your algorithm design on MATLAB Simulink, you have your algorithm design in either in the MATLAB or in the Simulink, but it as a hardware engineer, I know that it takes a lot of time to deploy that design on the hardware, and it follows a lot of steps manually. So as we know that hardware works on FPGA works very efficiently when it is working on the fixed point. So we need to convert the fixed point manually. Then we need to write the VHDL or Verilog code. Then we need to do the verification, and we need to FPGA verification. Then only we would be able to then only we would be able to deploy it on the hardware. And the main problem is once we write the VHDL or Verilog code, after that we do the verification, then only we would be able to find out the error. So that is very late stage. You have already written the code, you have already designed your algorithm, but you didn't find the error yet. So you need to go back to the algorithm and then you need to refine it again. So that's a very techy process. So for that, it's also very difficult to optimize at this level to like manually do it. So for that, we have this model based design for implementation. So what you can do is here you can write your algorithm in MATLAB script or Simulink. And instead of manually writing the code, you can automatically generate the HDL code, and which I have shown in the demo. So how you can do it? You can use our coder products like HDL coder, which will automatically generate the HDL code, and you don't need to write anything. It has VHDL or Verilog both. By default it takes VHDL code, but you can select the Verilog also. That I'll show you later how you can select the VHDL or Verilog code. So once you have generated the code, what will be your next step, right? The verification. So the verification will be your next step. For that, what you can do is you can do the behavioral simulation using a tool called HDL verifier. And that tool is also called as HDL co-simulation. So I'll explain these here. I'm just giving the overview. I'll explain these in the later slides. So just at this time being, just keep in mind that we can generate automatically the VHDL or Verilog code and can verify it with it on the same platform, right? On the MATLAB only. Then so after to basically now after generating the HDL code, what process we do is we synthesize the design, we check that it is synthesizable or not, we map the design, place and route, and then we generate a bit stream for hardware deployment. So it takes a lot of steps manually, and it takes a lot of time, right? So here to basically automate the process of generating bit stream, we have tied up with different major FPGA and SoC companies, which is like Xilinx, Microsemi, Intel, and so on. So what happens is like once you generate your code, you have to tell MATLAB that where is the synthesis tool present in your machine. Suppose you have installed the Vivado. So you need to tell MATLAB that this is the path for the Xilinx Vivado, which you can use for automate all this process. So what MATLAB will do at the back end, it will open the Vivado, it will synthesize the design, it will implement the design, and then it will generate the bit stream automatically. You don't even need to open your digital design project, or you don't need to open your algorithm even there. So you can directly see it in the MATLAB only. So so here for all this, the problem is that we can find the error at the algorithm. The problem in traditional one is that we find the error after the verification. Here we can directly find it at the design phase only. So once you have generated the bitstream file, we have added another level of verification, so which is FPGA in loop. In FPGA in loop verification, you port the algorithm on FPGA, you can get the result back from the FPGA into your MATLAB environment, and you can check the results against your algorithm simulation. So basically there you can test that is it even functionally working or not, even way before going to the to the actual hardware implementation. So this helps very much to verify your design instead of wasting the time to deploy it on the hardware, right? So what is the basically what is the advantage of this, what I why I'm telling you all of this, like why you can also have a students which can work on different aspects, but I'm telling it because the collaboration between, like I have worked in the I have worked on the same parts before also. So the problem is that one people is generating one people is writing VHDL code, one is designing algorithm, so the collaboration between those two are very difficult. So and sometimes miscommunication happens and your design goes all wrong. But here all of the students, all of the people are working on the same platform on a single GUI, in which like suppose this automatically this is doing the thing, so we don't need to so the collaboration between different students are very seamless. So for this model based design, we have been supporting a lot of government organizations like ISRO, SAC, DRDO labs, and multiple industries too. So they are now opting for the model based design approach. So I have a user case here. We have worked with Aurelia earlier, and they were making the emergency locator beacon SDR receiver. Earlier they were using it, they were preparing the implementation part with the traditional workflow, that they have their algorithm ready on the MATLAB transcript, MATLAB script, and then they were about to write the VHDL code. Then they contacted us for the implementation help, because they have a tight deadline or to deliver the product. So then we explain them that how this works and how model based design can help, which results them actually to reduce their FPGA implementation time by at least 50%. And they were able to deliver it before, even before the their product were ready even before the deadline. So after that they started using the model based design. So this is a just I'm showing that multiple users are using this design as it is helping them to reduce the time and efforts, and also the cost, of course. So basically, currently I have just given you the overview of model based design for implementation. Now I'll go to the HDL code generation part. So what is the HDL coder features? So first thing is that it automatically is the first thing is the code generation, and the second thing is the design automation. What is code generation means it what is code generation means it generally it generates target independent HDL code. So when I say target independent HDL code, I mean that MATLAB does not generate a code specifying to any hardware. Like this is the code for Xilinx, this is the code for Microsemi, this is the code for Intel. It's not like this. It generates the code in general. You can deploy it on any hardware. But the only thing is that you need to select the hardware there before generating the bit stream. So and it provides bidirectional traceability, resource utilization, critical path estimate reports, generate test bench. So you don't need to generate all the reports. You don't need to check your resource utilization and critical path estimate manually. So I'll just show you in a demo like how this does. And the design automation is basically, which I told you earlier, that it automates all the generation, all the bit stream generation process. So okay, let me show you a demo. I'll just close this one. I'll just close this one. Okay, so I'm going to show you the demo of this only. Okay, so here, so here for this we need the hardware support packages, which I told you earlier, that we need Xilinx hardware support package and whichever hardware you want, right? So I'll just go to the right click. Now, instead of going to the generate HDL for subsystem, I'll go to the HDL workflow advisor. So this HDL workflow advisor basically guides you to implement the design on hardware. It has proper steps how we do it, and then so I'll show you. Okay, so so you see that there is a warning, which is target platform Zware requires one of the following synthesis tools, Xilinx Vivado. So this is what I was talking earlier, that we need to provide the MATLAB, the tool path to the MATLAB to know that this is the tool which we are going to use, and this using this tool you can generate the bit stream. So I'll just clear this one. For that toolpath, for giving the toolpath, there is one command which you can search it like help hdl toolpath. hdl toolpath set hdl, yeah, hdl setup toolpath. So okay, let me this one. So how I did it, help space hdl setup. So if you know the command's initial letters, you can just write it and then press tab. It will directly show you the commands. So just enter it. You see, it will set up the toolpath. So it has all for all the Xilinx Vivado, Altera Quarters, Microsemi, Libro. So right now I'm using Xilinx Vivado. So I'll just copy it. So okay, till now, does anyone have any question or everything is clear? Just acknowledge, please.
I think later on we can they can have the query. So just you can proceed. Sorry. Yeah.
Okay,
Please.
okay.
Yeah.
So here I have 2020.1, which version is, we have the whole compatible list of Vivado and MATLAB. You can check it. I'll share the links after the presentation to Dr. Rohit, and then he'll share it with you. So I have 2020.1. So I'll just enter. So it will show as prepending following Xilinx Vivado path to the system, this one. So basically what happens is, now the MATLAB knows that I am using the Vivado 2020.1. So it will at the back end, it will use the Vivado 2020.1 to synthesize, implement, place and route and generate bitstream for the design. So I'll go here. Okay, yeah. So the very first step is set target. So here, okay, let me again open the Vivado workflow advisor, because I have. Okay, so now you can see that it didn't give me any warning about the tool and everything. Okay, so now this have the option of target workflow. So here, if I talk about the target workflow, there are multiple target workflows. So here I'm going to show you the demo of FPGA in the loop, but I'll just go briefly like what is there. So other is FPGA turnkey. So FPGA turnkey is you can select when you are already done your verification. You know that your design will fit onto the hardware. You can select that. You can select the FPGA turnkey because it will directly generate the bitstream and you can put it on to the hardware. Then the Simulink real-time FPGA IO. The Simulink real-time FPGA IO is basically more towards the control application, where you have a control model or a plant model and you want to tweak the parameters within the Simulink only, and within like a real-time FPGA, on the real-time FPGA only. So if those kind of applications you are working on, then you can use the Simulink real-time FPGA IO. The IP core generation workflow is basically when you want to put your design on some SoC like ZC706, Xilinx SoCs. So because when you select the IP code generation, our tool will know that the DUT, the device interface, which we want to implement on the hardware, that will go on the hardware only. The rest of the parts, which is outside of the DUT, will go on the processor. So as SoCs has FPGA and ARM processor, so it works for both. So here I'm selecting the FPGA in loop. This is the board list which you can select. Any of the board you can select. Currently I'm selecting the Z board. You can create the custom board also. If you have another board which is not listed here, you can create that. So I'm selecting here Z board. So synthesis tool, once I define the path in the command window using HDL setup toolpath, it will automatically take the synthesis tool. Like it took the Xilinx Vivado, it took the tool version is 2020.1. Okay, so this will be automatically selected using the Z board, which is supported basically. So this is the project folder which currently which you can browse from here also. Any project folder you want to implement it. Okay, so now if I run this task, so it is showing that I have already existing HTL underscore PRJ folder, because I have previously shown you the VHDL code generation using earlier. So that's why it has this. So if I want to replace it, then I can do it yes. Otherwise, I can replace it. I can do it no. So then we go for the set target frequency. So target frequency is basically on what frequency you want your design to work on. So currently I want my design to work on 25 megahertz. So I'll just keep it as 25. So I'll just run the task. This green sign means it passes the task. It does not have any warning. It does not have any error. Now, now this is the important thing is that here it will prepare the model for HTL code generation. So what does that mean is, suppose you are an algorithm designer, you don't know what blocks are going to be HTL compatible, what blocks are going to be code generatable. You don't know that. You just design an algorithm on Simulink, right? Or on MATLAB. So this check model setting will do it automatically. So this is the newer version of MATLAB. It's 2021b. But if you have previous one, so it has all here, all checks here. So you can check all the ports and subsystems, floating point checks, model configuration, industry standard, check for board, blocks and block settings. So this block and block setting will check what are the blocks are implemented. If not, it will give an error, and it will, if you will click on that error, it will directly replace that block by the compatible one. So okay, but if you have the previous version of MATLAB, I'll just show you how it will look. So okay, so it will show you like this. Okay, you can see my presentation screen, right? Yeah, so it will show you like this. Here you can check that in the prepare model for HDL code generation, there are multiple checks. So first one is check global settings. So whether it will check that all the global settings of your model, whether these are on point or not. So next is the check algebraic loop. In check algebraic loop, basically it will check any algebraic loop fault in your model. Like suppose if somewhere it is dividing by 0, or it is going infinity or like this, then it will give you an error. Then it goes for the check block compatibility. So in this check block compatibility, like I've earlier told you, that it will check for your model that the blocks are hardware compatible or not, these are code generatable or not. If the HTL block are not generatable directly, you can always, suppose I have a PLL block, phase lock loop, which is not code generatable. I don't have it in MATLAB. Now what should I do? So you can see like but there is always a way to generate the PLL block. Suppose I use the NCO, I use the multiplier, I use the low pass filter, and all these blocks are or HTL generatable. Okay, so by these blocks I can make my phase lock loop easily. So that will be the code generatable model basically. So then the next, it will check the sample time. So it will check that if there is any mismatch in the sample time in your model or not. Then it will go to the FPGA and loop compatibility check. So it will check your loop compatibility, that like suppose for Xilinx, it always communicates with JTAG. So do you have the JTAG IPs in place or not? Which is generally taken care by the support packages. So okay, I'll go back to the demo part. So here it does at the back end. So I'll just run this task. So here is the loop compatibility check. I'll just run this task. Now I'll come with the HTL code generation. So here we generate our VHTL or Verilog code. Now you see that I don't see any option of VHTL or to select the VHTL or Verilog code here, but I can see it here, HTL code generation settings. So here I can select here I can select my if I want the code in VHTL or Verilog, in which folder I want. Target I have already selected, so it will automatically take it. Optimization I'll go next I'll go later, like how we do the optimization part. It has by default some optimizations also, but you can do it more. Then okay, then these are the global settings, like you want to have the reset or not, you want to have the clock or not, it should be asynchronous or synchronous. Like this you can check how your reset level should be active high or active low, means if your clock, and also the clock, the input port is or clock enable or not. So basically if you're which, like at what edge you want your output, like, right? So like at high edge you want your output, or low edge, so you can select it here only. Then the report part, in which you can check the traceability report, model web view, resource utilization report, optimization report, and high level timing critical path. So you don't need to check the critical path in your design, that from where to where I need to get it and all. You don't need to check the resource utilization. You can do it here only. Then it will automatically generate the test bench also. So if I check the HDL test bench, it will generate it for the whole model, not only the DUT, the rest also. But if I select for the co-simulation model and DPI test bench, it will only generate the test bench for DUT, which is going to be on the hardware. Okay. So, okay, I'll just run this task. Now, this one, generate RTL code and test bench. This step will, so settings we have already given in the HDL options. This will generate the reports and test bench. So let me show you. Okay. Yeah, so you can check generate test bench and validation model also. You can uncheck it also. It will just show you. So basically, it will just show you the models. I don't want to see the model right now. Okay. Just it'll just take 1 minute to run. Yeah. So you can see that I got all the reports here. I have the resource utilization report, multipliers, adders, RAM, everything. I have the critical path estimation report. I have the traceability report. Okay, so I will show you, this is the VHDL file. Okay, so when I show you that in HDL coder we have the bidirectional traceability, what does that mean? That means if I go any block of, if I click on any block, it will show you where that is present in the VHDL code. Okay, so here these are the VHDL code for this block. For this block here, these are the VHDL. So this is one side. Now, suppose if I want to click on here, it will show you which block is this. So it is for delay. Okay. This is for this delay. So this is what is bidirectional traceability I was talking about, that you can go from the code to the block, and from the block to the code. Okay. So this is pipelining and everything. I'll talk about this later. Okay. This is just for the report generation and critical path estimation. So I'll just close this report. And then this is the FPGA in loop option. So as I have already told you that the Xilinx Vivado will always take the input from JTAG cable only. So we can run it here. Okay. Yeah. So currently I don't have hardware at my home. So I'll just show you a video of FPGA in loop implementation later. Okay, by connecting the hardware. But I'll go to this step later. Before that, I just wanted you to show the optimizations and everything, how we can do it. Okay. So yeah. Okay. So basically, with what optimizations we can do. So suppose I'm happy that my VHDL code generated it very quickly. I have my design verification and everything. But what if I'm not happy with the resources it is using? What if I'm having the lower version of the FPGA, which does not support that much of multiplier or that much of resources, right? So, and what if it is not meeting the timing requirement? So we can do the optimizations in case of timing requirements with area constraints. We can map it to the dedicated hardware also. We can reduce the latency. We can minimize the power, and we can maintain the after all the optimization, we can also maintain the algorithm functionality. So if we see the speed optimization and resource optimization, so in the so in the speed optimization, you can see that speed optimization is basically the estimate of the critical path delay. Okay, so if suppose if it is happening what is critical path delay is the time between the longest path time basically. So if I do the speed optimization using suppose it is using the sequential operation, what I can do is I can do the parallel operation. I can use the pipelining there to optimize my speed. And in the resource optimizations, like here, if I'm using the format, so okay, instead of showing you here, I'll just show you the demo part. Okay, so okay, let me show you. So right now, okay, sorry, I closed the report. I'll just run this task again so that it will generate the test bench reports again. Okay. Is it clear till now? Any questions or any doubt? Do you have any question, anyone?
No, I think we can take the queries at the last. Otherwise, they will write in the chat box if needed.
Yeah, okay. I'll prefer to
Yeah,
write it in the
yeah,
chat box, or
sure,
say to me in between, because it's a demo
sure,
partner. So I don't know in the
sure.
last it will be okay or
Mhm.
not. Okay. So, so yeah, I have shown you this resource utilization report, right? So now we can see that it is using multipliers as 4. Now, suppose I don't have 4 multipliers in my hardware. So what I can do is I can optimize the resources. How? From here. So okay, so I'll just right click on the DUT. Then I'll go to the HTL code. I'll go to the HTL block properties. Okay. Here I can select the sharing factor as the, like, suppose I want number of multipliers as 2. I have 2, then I can use it. I can keep the sharing factor as 2. If I want number of multipliers as 1, I can keep it as 4. Okay. So right now, okay, I'm doing it for the sharing factor, and you don't need to go again for the whole step. You just need to run this task. Okay. So it will again generate the report. Did it run? Yes. Okay. So now I go to the resource utilization. I can see that the number of multipliers are 1 only. The similar way you can do it for other parameters also. But okay, yeah. So so this is for the resource optimization. Now what if I want to do the critical path estimation optimizations, which is like the speed optimization. So currently, if you see, okay, currently if you see, these are the this is the it will also show you like from where I'm getting this much critical path. Okay, this will show you the whole detail. So this is the highest critical path which I'm getting, is this one here. Okay, so this is the critical path which I'm getting. So it will show you like this. Okay, so before going into this, I'll just show you how I can. So now I want my critical path to be less. Okay, so first I'll check like how much critical path was earlier, then how much it will be lower. Okay, so I'm just keeping it same to keeping it 0 to check the critical path effects basically. Okay, let me run this again. Okay. So right now the critical path is 9.944 nanosecond. Okay. So now I want to reduce my critical path. What I'll do is I'll add pipelining. Okay. Just so this again, I'll go to the HTL code, HTL block properties. I'll add the pipelining. So you can add it in the input pipelining also, or the output pipelinings accordingly, whatever you want basically. So according to your design. So suppose I want it here as 5, the pipelining factor. Okay. So now I'll again run the test bench. So So yeah, so you can see that the critical path delay has increased, right? Earlier we have 9.955, now we have 10.186. I'll tell you why. Why we have this is because input pipelining 5 as we have given, it has added it here as a lump sum. We don't want it. We want it distributed, then only we would be able to parallelize it, and then only we would be able to reduce the pipelining. So now for that, what I can do is I can just go back to the HTL properties, and then on the distributed pipeline. What it will do, it will distribute this five delays to the to according to the basically it will distribute the delay in to minimize the critical path delay. So I'll just off this one. Okay. Yeah, so now you can see we have earlier as 9.944, now we have 6.213 nanosecond, right? You can see the it here also. The lump sum z to the power minus 5 is now distributed in through the different z to the power minus 1. Accordingly, it has seen it. Okay. So this is what is optimization. You can do a different type of optimization also, which you can select it from here. The optimization part here also, the pipelining, like instead of, if you don't want to use the delays, you have more RAM, you can use it for RAM. You can select the different type of pipelining, you can select the different type of resource sharing. Okay, so this is if you want to reduce the multipliers, you can select it for multiplier. If you want to do it for adders, you can select it for adders. So there are multiple optimizations present. Okay, so now I'll go back here. Okay, so as I have told you that the resource, as I have shown you that the resource optimization part, so what it does is it we give the sharing factor as 4. So instead of all these 4 multipliers, it will create a 1 multiplier. Okay, and that's how it reduces the area constraint. Now for the speed optimization, basically, just a minute. Yeah. Now for the speed optimization, basically, this is the optimization method that improves the operation speed. Again, with the related to the critical path estimate. So as I have shown you that if I am giving as the pipelining as 2 or like as 5, as I have told you that it is as 5, so it will add lump sum of z to the power minus 5 here. But if I use the distributed pipelining, it will basically divide the delay blocks according to minimize the critical path estimate, and according to parallelize the design basically. So we can see that here 2 is pipelining factor. So it is divided into 2 stages of the pipelining stage inserted into a signal flow of the algorithm, right? One is this, one is this. Okay, so basically, from this perspective, if I see that it is a method of optimizing even while maintaining the functional characteristics, it won't lose the functional characteristics of the algorithm. So this pipelining will help you to maintain the same. Okay. So the one is adaptive pipelining, which generally it by default it takes. So basically what it does is it usually uses your target frequency and setting along with the delay estimates for components. Okay, so basically suppose if you have the target frequency of 500, so it will use this target frequency and insert the delay accordingly to match this target frequency, and the model will run at suppose you are inserting as 4, then 4 for adaptive pipelining, so the model in the end will run clock rate faster than the 4 times. So that's how it maintains the functionality of your algorithm and latency also. Okay, so this is till now I have shown you about the HTL code generation, how your bitstream generator. So okay, before that, before going to this, let me show you the FIL video. Okay, I can show you later. Okay, I can show you later. Yeah. So so till now I have shown you the HTL code generation part. Now I'll talk about the HTL verification. Okay. So we have HTL verifier as a tool for verification, which co-simulate the RTL back to back with the model to debug before FPGA deployment. As I have already told you that it deploys your design on hardware, then it gets back the algorithm from hardware to the system, and you can verify it with your actual algorithm design results. Okay. So also you can simulate the FPGA in loop for additional verification. And this is generate IP block on the FPGA. You can use it for SOCs for IP core generation, in which it uses the AXI as an interface between processor and the FPGA. Okay. So if you want to go for the SOC implementation, you can use you can use the IP code generation. Okay. So yeah. So now, first of all I'll show you that how the HDL this HDL simulator HDL for verification works. Okay, so we have our design in desktop in simulation. Then it goes to the HDL simulator that is also available on the PC. Then then it generates the design will generate the code using the HDL coder, and it compiles the code. And after it goes to the HTL simulator, it will give us this, it will give us some results. And how it will give the results, will use some test vectors from the input design. Okay, so these results will be compared with the results from the actual algorithm design. Okay, so this is an method of verification. And the another method of verification is the FPGA loop, in which what we do it is we have the algorithm on MATLAB or Simulink on our desktop. We connect it using either JTAG, Ethernet, or PCIe with FPGA, and then again the same it uses the test vectors from the input, and it generates the code and bit file also, which can be deployed to the FPGA. And the results we can compare it on the with the actual implementation. This I'll show you in the demo, which you can see. Okay, so you can see the demo here. So you can see here I am not using the Xilinx Vivado use because I'm sorry, I'm not using the Xilinx board. I'm using the micro semi board here, because this is a previous demo which I've given to some customer. And at right now I don't have any board on my house, so I'm showing you the video just to show the process. Okay, so here, if you see that we have already seen that I've already told you that the Xilinx Vivado takes connection of FPGA and loop through JTAG. Okay, so it takes the connection from JTAG. So what happens is, like, it will port a bit file, and the output of the bit file will be communicated back to the laptop. Okay, via Ethernet, right? So if you see, this is your board, this is the board, and this is now going into the laptop. Let me show you. Okay, this is now going into the laptop. Okay, so I just pause it here. I'll show you which of this is the design. Okay, I've shown you the demo here. Now, till now I have not built up the FPGA in loop. So this is the previous workflow which I have shown you. Now I'll build up the FPGA in loop. Okay, just let it run. But it will just take time to run because it is building the model for FPGA implementation. Okay, let it run. Till then, I can take any other questions if it is related to this, or if it is related to something else. I can take some questions if you want till it runs. Okay, I don't know why it is taking too much. Maybe because of the network issue. Okay, let it run. I'll just show you the next step till then in the video. Okay. Okay, so yeah, so this is the board. This is going to the PC. Okay, so this is basically the model which will be generated through that process, and like what I have run build FPGA model, this is what will be generated. So okay, so upside this one is the, let me show you. Okay, sorry. Yeah. Okay, so this is the model which we will generate using the FPGA loops. This upside model is our actual implementation, which we have done, and this is the model. The below model is the FIL model. Okay, FPGA loop model. So if you double click on this model, it will automatically take the TCL file, right? And it can sometimes it will automatically take the bit file also. So then you load the you load the bitstream file on the FPGA. Once it shows that FPGA programming file loaded successfully, you can you can check it on the check the results in here also. Once you run the simulation here in the FIL mode, you can compare the results with your actual implementation. So what you can see is the above one is the this one is the algorithm implementation, your actual algorithm implementation. This one is your FPGA implementation. Okay, and this is the error between these two. So right now like this is a basic example, we don't have any error, and should not be, it should match with the FPGA implementation, then only we can say that it is working fine, right? So this is what this is how we do the FIL simulation. So that's why I was saying that it is an additional step for the verification, because you can easily check that how your FPGA design is working on the with the uh, uh, your actual implementation design. Okay, so yeah, so this is I can say this is the key takeaway for you, that with this model based design implementation, all the steps from this all the steps are in one single GUI. You don't need to collaborate with the collaboration is very seamless. Okay, so this is basically generating the bit stream, that's why it is taking the, okay, yeah. So this is basically what we have clicked on the build FPGA loop. This is the model which I have shown you. Okay, this is the model of your actual FPGA implementation, which you have like put the delay pipeline and everything. This is the model of FIL1. So here, if you double click it on, it has already taken the bit file, as I have already told. Once your hardware is connected to your laptop, in which this is present, you can load the bit stream to the hardware. So suppose if right now I load it, then it will say that no hardware connection. Okay, and this so what I told you, that it will use back at the back end, it will generate the bit stream and everything. So it is doing the same thing here, synthesizing, implementing, and everything. Okay, so once it will be completed, then only we can run the we can load the bit stream to the FPGA, because right now it's just taking the path. Right now it is not taking the bit stream because it is not generated yet. Okay, so I'll go back to the, yeah. Okay, so this is what we can do is when we don't have, like when we are not having any SOC or anything. Suppose I have SOC, suppose I have programmable SOC. I want to implement the design. I want my algorithm. I want some part of my algorithm to be implemented on hardware, some part of my algorithm to be implemented on processor. So what I can do is HDL coder will generate the HDL, VHDL or Verilog code for the FPGA part of your algorithm, and embedded coder will code the C or C will generate the C or C++ code to your processor part of the SoC, and also other processors. Okay, ARM processor or DSP MCU. So these are the two tools which are mainly used for code generation and implementation. Okay, so now what are the key takeaways? What do you think is the advantage here? So we can say that this has the integrated workflow which increases the collaboration. It has a single test bench. You don't need to write the test bench. You don't need to to check it again and again. It also you can also automate the optimization of the design, which shortens this iteration cycle. It has a unified design environment because we have a very easy design entry and exploration. We have this PD simulation, as you can see, like it, like within even within the half hour, you can generate your model with test bench. You can deploy it on the hardware from algorithm level to the deployment level. Okay, so it has built-in analysis, as you have already seen. So that's how it shortens the iteration cycle, and it is more accurate because there are multiple level of verifications included. You can do the verification on the design level, in the design phase only. You can do after the code generation. You can even do before the before going to the hardware. You can do the verification to check. Okay, and it also increases your reusability. Suppose I want to suppose I want to change the coefficients there. Suppose I don't want the fixed coefficient. Instead of giving the fixed coefficients there as I've given in the input, instead of that, I can generate the coefficients there and give that into the FIR filter input, and again follow the same process. And I don't need to, basically I don't need to go suppose I change the coefficients. I don't need to write the VHDL code for those coefficients again. I don't need to write the test bench again. So this will automatically do the thing. So that will shorten your time and effort a lot. Then the verification basically reduces the verification time and early error detection, and it co-simulate with the HTL simulators and FPGA hardware, which helps you to verify your design and deliver it more accurately. Okay. So, in addition for FPGA, ASIC, or SoC related solutions provided by Mathworks, you can prefer to the links at the top of the data. Okay, so if you have any additional questions for development, you can easily contact us. Okay, and also you can go for with the seminar links. So these are multiple seminar links. I'll show you more. These are the learning resources in which you can go for videos and webinars, tutorials, MATLAB Central, on-ramps, and instructor-led training. So these are all there in the MathWorks. Okay, so there are some on-ramp course. If you are starting with the Simulink, this is the best thing which to go for. Even I started in the same manner. Earlier, I also used to do the VHDL and Verilog coding by myself, but now I do the model-based design. So this is like my own experience I'm sharing. So these are the on-ramp courses which you can take to start with: MATLAB on-ramp, Simulink on-ramp. And the good thing is that it has mostly all the fields HTL compatible blocks. It has machine learning, it has deep learning, it has control automation, all the HTL compatible. It has computer vision, image processing, neural networks, everything is there. Okay. So any of you, anyone working in different field can use the HTL block compiler, and there are different variety of sets are present there. So suppose if you are working in the wireless communication, you are working in the LTE, F5G. So we have 5G NR block sets there. We have encoder decoder blocks directly there in HTL generatable blocks there. So if you want to design an end-to-end transceiver, you can easily design it using this. Okay, so these are the training services which Mathworks provide if you want to learn more about this. Okay, so any questions till now? So you can, if you have any questions later, if you are planning to implement something, you can contact me, or this is our account manager who handles the account. You can contact him also directly. For any technical questions, you can contact me. No, I'll be there. I'll be happy to help you. Okay, so yeah. Okay, so right now, so I'm just showing that right now it has generated the bit stream, so you can load it. So any questions till now? Any questions you have?
Participants, any questions are welcome.
Is working on crack.
Yeah,
Okay.
someone is asking something.
It is working on crack version also. Yes, most of them can work in crack version, but if you have specified, like suppose if you want to use LTE or 5G tools, you need to have the license. So like simple HDL coder and you can HDL verify, you can easily have on crack version also. But if you want more, then you need to take the license. Any other questions?
I think we can continue later on. We can see.
Okay, so right now I have this. I can first thing I can show you is the learning program. So if you want any documentation, if you want any documentation part, you can directly go to the Mathworks website. You can use this documentation, tutorials, examples, videos, webinars, and trainings. Everything is there. Okay, so okay, so one of you has asking the crack version. You can also use the trial license. Okay, so that is provides for 30 days trial license. So if you want to get start, if you want that it will be helpful for you or not, you can install the trial license. It will have all the package. You can easily install the packages and everything. And sometimes it happens that when you are installing the packages, you don't basically you don't have the sometimes it basically Mathwork collaborate with third party tools, right? So sometimes it gives error to install the third party tools, but for that we have another alternative is to download them offline. Okay, so if any one of you trying to do the install the hardware support packages, and if you are giving error, please do let me know. Mail me, I'll send you the offline link there, which from where you can download, and it won't give any error. Okay, also okay, Dr. Rohit, I have this much for the implementation. I can show more towards the block set, but I don't know like okay, so I don't know how it will take place. So just suggest something basically. So do you want me to show, okay, any of the participants, do you want me are you on already working on this Simulink or anything? Any any participant, you can raise your hands, I can see it. Okay, so any of the participant is working on the hardware side? No one? Okay, so anyone is interested to implement the design on Simulink or HDL coder, or like not Simulink exactly, or any one of you working on the MATLAB? Okay. Okay, so I can just brief. Yes, ma'am. Okay, Abhiranjan. Okay, so okay, so I'll just briefly show you the block sets which are available on in MATLAB. Okay, so just let me present the screen. So you can go, okay, so first thing is how you can design the implementation. So okay, let me show you like how you can design the symmetric FIR filter. You have a design, you have a algorithm ready with you. This is the library browser from which you can take the blocks. Okay, so this has mostly blocks. All these, this Simulink block is not supported with the HDL coder. So HDL one is different. So it has aerospace block set. If any one of you are working in aerospace side, if anyone of you are working in deep learning side, so it has a deep learning toolbox. Okay, all these image classifier, prediction, and everything. Then if you are working in the DSP system, it has the DSP system toolbox. Okay, so here we have the filtering, adaptive filtering, multi-rate filterings, multiple filtering options. So now suppose if you have the suppose if you want to implement the filter on HDL support, so this is the DSP system toolbox HDL support. When you install the packages, it automatically these blocks automatically comes here. Okay, so these are like, this is the filtering, so it has multiple filters. Okay, bi-quad filter, any of the filter you can design using the HDL support. These are the mat functions which you can use. So also the good thing is that you don't need to worry about the fixed point. It automatically converts your design in the fixed point using the fixed point designer which we have. So in HDL coder also you have multiple, all the math functions and everything. Okay, so if you want to search anything here, suppose you want to search multiplier, let me show you. Yeah, suppose you want to search multiplier. So you can see that multiplier are there in the Simulink also, in here also. Okay, so yeah. Sure. So suppose you want to show header. Okay, so here you can see that whatever is include the header part, it will show you here. Okay. Hmm. So if you want to do end-to-end transmission or reception, you can have the RF block set. 89361 is the simulated one which you can use directly. Also, there are multiple wireless HDL toolbox. There are Vision HDL toolbox, UAV toolboxes, SoC block set, which I was talking about. That you can directly go for the hardware implementation side. Okay. So one thing I want to show is the 5G. Okay. So I'm expecting some of you are working on 5G because it's a very current topic. So if you see that there is like it is very hard to design the LDPC encoder, polar decoders. It has all the blocks here: LDPC encoder, polar encoder, decoder. Same goes for the LTE also. Okay. So okay, yeah, just yeah. So it has all the communication part: MIMO fading, CISO fading, rectangular pulse filter, PN sequence generator, fading channel. Right. Okay. So it has again the filters part. So, okay, so I think I have not installed the LTE part because I'm not working on it, but you can install the LTE support packages and it will definitely show you here the LTE toolboxes. Okay. So for right now, I'll stop here only because if you start working on this, I can definitely give anyone another session for this. So any of you have any questions for this, I can help you regarding this. So like how you are going to implement, how you're going to start with any of the questions I can take.
Guys, so I think from your side it's done, right, Niharika?
Yes, I am.
Yeah. Yes,
Yeah,
yes, done
I
with
just
that,
wanted
right?
to give the basic idea about how
Yes,
it
sure, sure,
works.
sure.
So yeah.
So, guys, from your side, just there is any query, if can ask, so we'll be happy to answer it, right?
Yes.
Or if there is no query, so I think just Niharika has given you her email ID. So
Yes.
just in case of any query, feel free to write her anytime for any kind of help. Right? She will be replying for sure. Right? Right? So just last time I'm asking if there is any query. Otherwise, we will stop over here on.
Please share one more time. Email ID you're asking for? Your email ID. Okay, I'm writing
Okay.
it here
Okay.
also.
Mm-hmm.
Okay. Please feel
All right.
free to contact me for any help or any discussion, anything.
Okay. So any other query? No. Okay, then we will stop over here by saying thank you to Niharika for giving a wonderful session, right?
Thank you
Okay, thank you
everyone
so
for
much, participants. See you in the next session at 2 p.m.,
yes.
right?
Thank you
Thank you,
everyone
Niharika.
for attending the session and
Okay, thank you so much.
thank you.
Bye-bye. Bye.